So the first six assumptions that we had were mostly green. One of them was yellow, and even there, because most of the time we are within the linear limits, so we said that those are all essentially ones which are satisfactory, both from the two types of questions that we asked about the necessity of the assumption as well as the relevance of the assumption. So from both these points of view, those were kind of okay. Now we get into the gray area where these are assumptions which are very, very commonly made, even in the aerospace industry sometimes, and kind of questionable in many cases. And the first one amongst them, which is something that many of you are already familiar with, the plane stress state, and that we typically write using the stresses, because that's what it is defined after, because it says plane stress. So obviously we have to identify a particular plane, and on that plane you have to have all these stresses. Out of that plane you're not going to have that stresses. So suppose we take that plane as the let's say the x1 x2 plane, in which case x is the direction which is the out of plane, and you do not have any stresses corresponding to that. So in other words, this can be very simply stated as sigma I3 equal to 0. So that's what it is. So if you have, let's say, the plate like this, so you have a plate like this. So what you're saying is that this thickness is typically small. This could be, let's say, the cover skin of the wing or the fuselage or the empennage, or it could be, for example, in the, let's say, if you have an eye section for the spar. You could be talking of any one of these flanges, for example, or it could be the web. So all of those are essentially thin plate-like structures. So these thin plate-like structures are the ones in which you're introducing in any one of them, along the thickness direction, you're introducing this x3. For this particular component, this would be the thickness direction, you're introducing x3, and for this, you're introducing an x3 over here. So if you are doing something like that, then what most people do is to take a plane stress approximation and take sigma I3 equal to 0. In reality, what happens is, this is, let's say, the cover skin of an aircraft, let's say a cover skin panel. Now this cover skin panel, if this is the outer portion, and this is the inner surface, you know that the outer surface is essentially subjected to a distributed pressure loading coming from the airflow that is happening over that, right? And it's also having actually, because of the viscous flow, it could be having certain shear stresses also coming from that, right? So some tau that is there. Now if you actually look at the stress according to this particular coordinate system that we have introduced, P is nothing but a sigma 33, right? Sigma 33 at a particular value of x3. If we are saying that this thickness, total thickness is h, and we have taken the x1, x2 along the mid surface of this plate or shell, then you're talking about a maximum of plus h by 2 and a minus h by 2 at the bottom. So you're saying that at x3 equal to plus h by 2, this is the boundary condition that has to be satisfied, because that is the pressure that it is actually facing. And whatever could be the interior, it could be, let's say, a fuel tank, it could be something else coming over there, it could be attached to the spar itself or the stringer. So that pressure or stress from the component which is attached to the bottom is coming there. So in other words, it's also not a non-zero stress value. So it's quite clear that the very boundary condition itself is not being satisfied by this. Leave alone what is happening in the interior, we still don't know. But at least we know at the top surface and the bottom surface, it is not actually 0. Sigma 33 is having a certain finite value, and it's compressive typically because it's a pressure, which means it's a certain negative value that it's supposed to have, but we are essentially taking it to be 0. So that is the problem that, which is why we put this in red. That is the first thing. That is, even in the healthy situation, we see that the problem with this is that and you can also go into a little more detail into the theory of elasticity. You can also show that some of the compatibility equations are violated. But what is most significant for us when we are in flight vehicle structures using composites in particular is that we will be using it in fashion like this, which means not a single layer but a laminate. Here we have just shown about 1, 2, 3, 4, 4 layers, but typically you would have 80, 100 layers in many situations, large transport aircraft for the cover skin. So when you have something like that, it's very clear that there is going to be an interface between each layer and there is going to be a stress, and all of those interfaces are having the x1, x2 plane. In other words, x3 is perpendicular to that. So the interface stresses are always going to be these three guys, because here I equal to 1 to 3 over here. And sigma 33 is the normal stress, so what we call as the transverse normal stress. And corresponding to these two, you are going to have what are called as the transverse shear stresses. This is from the perspective of a plate or a shell. In the case of the beam, it will be slightly different, what we call as transverse. So we'll come to that a little later for this situation. But even here, we can analyze it as three separate plates out of which this spar is composed. So when you're talking about that and introducing your x3 thickness direction in each one of them as shown, then it's very clear that these are the transverse shear stresses from a plate theory or a shell theory point of view, and this is the transverse normal stress. And that is what will be at the interface over here between the first and second layer, similarly again between any nth layer and the n minus 1 and n plus 1 layer, that in those two interfaces that each layer has in general, except for the top and the bottom, all those have to essentially balance each other out in terms of the stresses, because there's nothing else which is coming in between to provide that additional stress to balance out in case they are not equal to each other. So the very fact that on the top of this you have that boundary condition coming in from that pressure and the viscous stresses coming in tau, which means that at this, because it's a fairly thin structure, you will not typically go to 0 already. So you will have a certain non-zero value, and that has to be balanced out by the second layer and so on and so forth. So, and in when you take the composite structures and typically look at their failure, apart from the failures within the ply, one of the most common failures is delamination. So where two layers are getting separated out. So we call that as delamination, because the lamina are getting separated from each other, right? Now this delamination, if it were to occur, very clearly, you have a certain strength of the interface, and that strength is being exceeded in terms of the stresses that are being applied over there, right? So what we are talking about is either it is getting peeled out, which means that the sigma 33 value is over and above the peel strength of the interface, or the transverse shear strength is getting exceeded by the actual shear stress between two layers at the interface. So which can also result in it. In general, what could happen is all three are present simultaneously, and even though each one of them may not be as high as the individual strengths in those directions, as a combination they might cause certain delaminations to occur. And this could be at edges, what we call as edge delamination, or it could be internal, what we call as internal delamination. Now, if we were to determine that failure, which is very essential to understand the strength of this laminate, then if we had made this plane stress assumption, then we would not at all be able to detect delamination, because that would always say this is equal to 0, and therefore it's always safe because it's well below the failure strengths of the interface, either in shear or in peel. So the delamination is not accounted for. Is the third problem that you have with this assumption. But in reality, why do we make this particular assumption? What is the significance of this in these kinds of situations where you have a thin structure? What is the logic behind making this particular assumption? Anybody?
It makes analysis easy.
Yes, that is true. So that is what could come under this, what we talked about as necessary, even though it may not be relevant, it might be irrelevant because of these three reasons. You're still making it because it's making it simpler. So that's a very good reason. So amongst all the plate theories that you have, this would be the simplest. Just like in amongst all the beam theories that you have this so-called engineering beam theory or Euler-Bernoulli beam theory. This is what you have in the case of the plate theory, where you have a plane stress state and you're considering that. Now, this would have been okay if these were not there. In other words, the loads that are applied are not on the top and or bottom surfaces, but instead in the plane of this structure. So in other words, if I was only applying loads like this, either tensile or compressive, and shear loads like this, let's say, this is the actual applied load on this particular structure, then you see that all the loads are such that only the in-plane stresses are getting excited. But that is the case for isotropic materials. In the case of anisotropic materials like composites, what happens is that even when you are applying such loads, it is possible that some of the other loads, other stresses might get excited because of the couplings that happen between these different directions. It might not be the case if you had all the fibers along this, or even along this for that matter. You had cross ply, let's say, then the principal material directions are along which you are applying these stresses, and therefore the couplings will not occur in the other directions, and you might still be okay with that. But what happens in reality is that those loads, even though those loads might also be there, this is one of the dominant loads that you're going to have, and that dominant load will cause these sigma I3s. By the very boundary condition to start with, and also between the interface continuity conditions in terms of the stresses. For both those reasons, you will find that sigma I3 is actually not equal to 0. But it's not only the fact that it is simple. Yes, it is simple, and that is good. But there's another reason why this is used many a times, and that is the fact that you have sigma I3 in reality very small compared to sigma alpha beta. Remember, these are the alpha, any Greek symbols, as I already told you. We will take it, unless otherwise stated, as just 1 and 2. So what we are talking about are the in-plane stresses, sigma 11, sigma 22, and sigma 12, right? So we call them as the sigma 11 and sigma 22 would be your in-plane normal stresses, and your sigma 12 would be in-plane shear as opposed to what we already looked at, transverse shear. Now these will be typically much larger in magnitude compared to the magnitudes of sigma I3. So what we are talking about is actually magnitudes, because some of them can be negative, so it's important to talk about that. So what we are talking about is the magnitudes of these two quantities. So why is that so? If you look at this, a very simple example that you can take or think of is a pressure vessel. In a pressure vessel, if you have, let's say, a cylindrical pressure vessel, you know that it's the stresses in the longitudinal direction are PR by 2T, and in the circumferential direction, what we call as the hoop stress is PR by T, right? So now if you look at that, in this case, what we are talking of is H. So PR by 2H and PR by H, right? So this is the hoop stress. Now, whether it is the longitudinal stress or the hoop stress, you see that there is an amplifying factor for the pressure, which is R by 2H in one case and R by H in another case, where R is the diameter, the radius of the pressure vessel, and these are typically thin pressure vessels that you use in aerospace as well. A fuselage itself is like a pressure vessel because it's internally pressurized for aircraft flying beyond a certain altitude, cruise altitude. So you typically will have internal pressurization if it's a passenger aircraft, right? So that pressure, you see, that is getting amplified by the radius of the fuselage times the cover skin thickness, which is H, which is very large factor. And this is what would be your these two stresses, the sigma 11 and sigma 22 is what you're talking about over here. So sigma 11 is that and sigma 22 is that, whereas your sigma 33 on the top is just P. So you can very easily see that this condition that we're talking about, that's magnitude of sigma I3, which is of the order of the pressure. This is of the order of the pressure times amplifying factor, which is the radius divided by the thickness, and therefore you can very easily see that this is holding good. And that is the reason why, even if you take it to be 0, you are getting results but close to what is reality, but not exactly. And all these violations that are happening in many situations might be reasonably within the limits that of acceptable limits, especially when you're doing a crude analysis like a preliminary design or something like that. But once you get into detailed design, or you're doing more advanced analysis for checking specific materials and or looking at particular combinations of the angles that you want to have, how many plies you want to have, what order you want to put them in, the permutation is also important. So all those decisions cannot be made with this kind of an assumption, because you will arrive at erroneous conclusions, and you might end up with a non-optimal design, whereas with a very small change in the whole analysis paradigm, without this assumption, you would be able to do it. And it's not all that difficult, even though, yes, this is the simplest. In terms of the next step, what we need to do to look at the more advanced theories, it's not all so complicated once we understand the whole paradigm into which, or the framework into which all of these fit. So that is the reason why it's very important for us to understand the relevance of each one of these assumptions, and always make a check to see how large these quantities are. P might be small, but your tau in some situations might be beyond a certain level, and as a combination, the P and the taus in both the directions might be something that you need to be worried about. So in any case, even if they are small, you are taking it as 0, which means that all of these issues you have to live with, and whether that particular kind of analysis that you're doing, what is the takeaway from that? Is it all right with the violation of these things? These are the decisions that we as engineers need to make before we go ahead and make this particular assumption. So are there any questions before we move on to the next assumption? Okay. So the next assumption that we make is what is known as the Kirchhoff-Love hypothesis. So this is very similar to the Euler-Bernoulli beam theory that we have. So, as we already said, the simplest model of plate is what we are looking at as we proceed now. And till here, most of the assumptions that we were making were related to the material. Now, there is something that is coming up with respect to the geometry as well. For example, in the previous case, we talked about a thin structure, whereas here we will take that forward in terms of understanding how the deformations or displacement are going to vary, in particular from the point of view of the strain. So, here what we are going to say is that already from here we have said that your sigma I3 equal to 0. Now, we are going to go ahead here, and so what remains is only sigma alpha beta, and therefore, what is a direct consequence of that is your gamma alpha beta, that is the in plane strains, 2 normal and 1 shear, right, in plane shear. Now, this gamma alpha beta, we want to make a further assumption, which is what is stated over here, that the in plane strains are linear in the thickness coordinate. So, going with the same coordinate system of x3 along the thickness, what we are saying over here is that your gamma alpha beta, which is actually also a 3-dimensional stress measure number. So, it's a function of all 3 spatial coordinates and time also if it's a dynamics problem. Now, we are saying that this is equal to epsilon alpha beta, which is a function only of x1 and x2 and is one of the 2 terms that you have. The second term being x3 times rho alpha beta, which is a function also of only the in plane coordinates x1 and x2. So, in other words, what we are saying is that in reality, gamma alpha beta could be an arbitrary function of all of these 3 independent variables that you have. Typically, you have 4 independent variables including time, but 3 spatial variables. It could be an arbitrary function of x1, arbitrary function of x2, arbitrary function of x3. But what Kirchhoff and Love made an assumption is that in the thickness direction, the range for the x3 values is only from minus h by 2 to plus h by 2, and h is very small compared to L and B, the length and breadth of that panel or shell, and therefore, whereas it can still remain arbitrary functions of x1 and x2, with respect to x3, it can be only a linear function. It cannot have higher order terms like quadratic, cubic, etc. So, typically it's like a power series that you're talking about, and you're truncating it with just 2 terms, the constant term and the linear term that you are having, and you're saying that this is all that is. So, you are essentially dropping off all of those higher, so-called higher order terms. Now, this particular assumption that you have is very similar to what you have in the case of the Euler-Bernoulli beam theory, because I said that the Kirchhoff-Love plate theory and the Euler-Bernoulli beam theory are very similar to each other. So, let us go ahead, because you have looked at the simple engineering beam theory in your strength of materials course, let us revisit some of the assumptions that you make in that particular theory, and then we will come and compare it with what we are talking about over here, right. So, what are the assumptions you typically make in the Euler-Bernoulli beam theory?
Before and after loading will be the
Repeat that again.
plane sections will remain plane before and after loading.
Okay, very good. So, that is the first assumption that you typically make. Okay, what else?
Planes that are perpendicular to neutral axis will remain perpendicular.
Very good, yeah. remain perpendicular after the deformation as well. So what this typically means is that when you have, let's say, a cantilever, for example, you're taking any particular cross section at some value of x1 equal to x1 star, and that cross section you are following what happens to it after deformation, and you are saying that that cross section is like this. So one is that it was plane to start with and it remained a plane after the deformation. The other thing is that the normal that was there, the neutral axis was normal to it, continues to remain normal over here, right? So those are the two assumptions that you're making, which essentially simplifies the geometry in terms of the strains, how they are a function of, in particular, the, let's say, x2 is this coordinate. So with respect to x2, how it varies is what we are going to take into account. So in other words, this angle that has of rotation that has happened because of this, which is an angle theta, in terms of that you can get the displacement variables, and that is how the strains are also eventually expressed. In particular, the gamma 11 strain is expressed in terms of that rotation and the translation that is happening. And if you know the strain at any particular location on a cross section, you will know for all other points on that cross section by the fact that it is remaining plane and is just going through a rotation almost like a rigid body. Now, in reality, this is not a rigid body motion, because a different cross section, for example, a cross section here is not undergoing any rotation at all, whereas this cross section at the tip is undergoing much more rotation compared to this. So different cross sections are getting rotated by different amounts. So that's why we call this kind of a motion not as rigid body motion, but rigid body like motion. So it's somewhat similar to rigid body. Of the cross section. So it's not the beam which is moving as a rigid body. Well, that could be too if it's part of the vehicle and the vehicle is moving. It could be a rotor blade, let us say, which is moving with the helicopter. So there is a rigid body motion that is happening, but the kind of motion that we are talking about over here is made out of certain elastic deformations that are having with respect to a fixed end, which could be the hub of the helicopter rotor. And with respect to that, there is a translation of that cross section, and then there is a rotation of that cross section, and that's it. We are not talking of any other potential deformations which could happen. But we know that even in the simplest case of isotropic materials like metals, which many of the older helicopter rotor blades were made up with, you know that there is something called the Poisson's ratio and therefore the Poisson's effect. So if there is a sigma 11, you know that there is going to be not only a gamma 11 because of that, but there is also going to be a gamma 22 and gamma 33, which are unless and until the material has a Poisson's ratio of 0. So in all those situations, very clearly we see that we are violating something, because in addition to this, though many books may not state it specifically, we are also having this rigid body like assumption of the entire cross section. In other words, it's not allowed to deform within its own plane either. It's because plane section remains plane means that it is not allowed to deform out of the plane. The other thing is that within the plane also it is not allowed to deform, because it's a rigid body like. The Poisson's effect is completely assumed to be 0 or neglected. So that is the similar thing that we are trying to do here when we invoke the so-called Kirchhoff-Love assumption or Kirchhoff-Love plate theory. Many times it's called as the hypothesis, because based on this particular strain, essentially what you're saying is that where here you're talking of a cross section. What is the equivalent of a cross section in the case of a plate or a shell? If you were to extend these same assumptions there, what would we be talking about? Here we were mainly talking about the sections, right? what could we be talking about in the case of a plate theory? Mid-plane, mid-surface, that is equivalent to your reference curve. So what you have here is called as a reference curve. If it's a straight line, you could call it a reference line, but typically it could be an initially curved beam also, so you're typically talking of a reference curve. The equivalent of that reference curve in the plate theory, analogous to that, you would have a reference surface in the case of a shell, or a reference plane in the case of a plate. Okay, so here also you would have either a reference line, which in more general case you're calling it as a reference curve, right? So those are equivalent to each other, but the cross section is not equivalent to that. What is the cross section equivalent to? It's the smaller dimension that we're talking about. Remember, what are we talking about as a cross section is that there is one larger dimension. I'm leaving that larger dimension out. Only the smaller dimensions I'm taking into account. Therefore, I call that as the cross section. Okay, and that's what we are dealing with, and all these assumptions are associated with that, because I can say certain things about the smaller one, and the larger one I'm still allowing for the theory with all of its complications to go ahead. I'm just only on the smaller dimension, because it's so small, I can make certain assumptions. That is the whole idea behind this kinds of hypotheses, right? Now, so the smaller dimension there was the cross section. What is the smaller dimension in a plate or a shell? Thickness, right? So here, what we are talking about is, instead of a one-dimensional entity, we were looking at a two-dimensional entity. Now it's getting reversed, okay? So now instead of a cross section, which was in the beam, cross section is in the beam. Now beam is to shell. If you're talking of, here we are talking of a normal to the surface, right? So a normal line which is perpendicular to the surface. Now we are taking that, and we are taking that line, and whatever we were saying about this section, we would now say about this. In other words, we were treating the section as a rigid body. We are saying it remains plane. Here we will say the line is a rigid body, so it was straight originally, it will remain straight. The other thing we said that it was perpendicular, and now you are going to say that originally the line was perpendicular to the reference surface of the plate. Even after deformation, it remains perpendicular to the reference surface. So those are the two things, direct carry out, and if you look at those and you connect your strains to the displacements, because the strain and displacement, as you know, are related to each other as the derivatives of the displacement with respect to the spatial coordinates, and if you see, this is exactly saying that. So you can work backwards and see, you take each one of them, gamma 1, 1, gamma 2, 2, and gamma 1, 2, and you see if it is linear in X3, what exactly it means. It exactly means that this particular thing is acting like a rigid body. First of all, it cannot have any change in size, which is what we were saying the Poisson's effect is violated over there. Same thing here. If I stretch the plate in either direction, I should expect the thickness to contract from the Poisson's, if it's a typical positive Poisson's ratio for conventional materials. Then this is not happening over here, that you are keeping the size, the thickness the same. You're also keeping it straight. So in other words, that plate that you typically have, it could in general have all kinds of deformation, and that normal that you had to that could in general have become like this. So we are avoiding all of that thing that is happening and saying that it is only the straight line as it is. At the most, it's having a translation and a rotation. So in other words, just like the cross section, it could have a translation and then it could have a rotation. Similarly, the straight line, it is having a translation and then it is having a rotation. So that is all that is allowed. It is not allowed to change its length or become crooked like this. In other words, what we call as warping. So essentially here you would have studied in when torsion is applied to non-circular cross sections, the plane section doesn't remain plane, it warps, right? Let's take a rectangular eraser, for example, and you try to twist it, you will see that the cross section goes in or out at different locations. Its plane section doesn't remain plane. That alone is typically called as warping in a typical undergraduate course or an undergraduate textbook. But warping is actually a three-dimensional field. So, in other words, just like displacement, we have the concept of a 3D warping where there is an out-of-plane warping and there is also an in-plane warping, the simplest in-plane warping being Poisson's effect. You know that in Poisson's effect, different points are going to be moving by different amounts. In other words, it's no longer a rigid body-like motion within the plane as well. So, while you could talk of the warping in this case along x1 as W1, you would talk about the warping in the case of the within the plane, cross-sectional plane of the beam as W2 and W3 in the x2 and the x2 direction and the x3 direction. Similarly, in the case of this also, you see that it's not only a translation and rotation to this, but in general it could be something like this, which means that motion that is happening is a three-dimensional motion, and in general you could have a W1, W2 and W3 associated with that. W3 referring to the change in the length of that normal line element, and W1 and W2 making it no longer a straight normal, but you are having a crooked thing like this. And in addition to that, we said that here it was a 90-degree, right? That rotation that you're going to have. In general, what could happen is that there could be a rotation of the cross section. First of all, let's say that cross section takes a joyride on the reference curve. You have a reference cross section on a reference curve. The reference curve is changing from this to this. When it changes from this to this, along with that, that particular cross section comes and takes a joyride. Now, over and above that rotation, because of the reference line rotating, you could also have an additional rotation, which means that this angle is no longer equal to 90 degrees. It could be either slightly larger than 90 degrees or slightly less than 90 degrees. In other words, this particular assumption is getting violated, right? Now, what that means is that there is a certain transverse shearing strain happening. So, in other words, there was no transverse shearing strain in your original assumption of the Euler-Bernoulli beam theory. The only difference in going from Euler-Bernoulli beam theory to the next best very popular beam theory, namely the Timoshenko beam theory, is to allow for this additional rotation to take place. That's one of the major differences between the EB theory and the Timoshenko theory, right? Now, that can either be taken into account in that way, or it could be lumped into your 3D warping. So, there are two ways of looking at it. So, in other words, that rotation of the additional rotation of the cross section over and above the reference curve can either be thought of as an independent degree of freedom, or it could be lumped into two of the warping measures, because there are going to be two rotations. One is rotation with respect to this, and another is a rotation with respect to this, right? So, these are because of two kinds of transverse loads. One is along the x2 direction, the other is along the x3 direction, which is perpendicular to this, which is going to be pulling the beam out or into the plane of the board. And when you're doing that, there is going to be a rotation which is associated with that as well. Now, those two rotations, there are two ways of tackling it. One way of tackling it is like the way Timoshenko did it, by introducing new degrees of freedom, which is in addition to the three translations that it can have, the three rotations that it can have, two rotations being because of bending, the third rotation about the x1 direction because of torsion, right? So, a rotation about x1 is torsion, a rotation about x2 or x3 is due to bending, okay? And there is a translation along x2, a translation along x3, which is also happening because of bending, okay? So, bending is causing two kinds of effect. One is the translation along the x2 and x3 directions, depending upon the specific direction of the bending, and in addition it is also causing a rotation. But in the simplest case, it would cause a rotation such that it would, the cross section would remain perpendicular to your reference curve. But over and above whatever rotation is there, that is what is your transverse shear rotation that is taking place. Now there are two ways of tackling that, as I already said. One is Timoshenko's way, where you introduce, in addition to those three translations and the one rotation only that you are taking into account, that is around x1, because the other two rotations we were saying is dependent on the translation, because the derivative of the translation with respect to x1 is going to give that, because it's just having a joyride on the reference curve, and therefore if I know the translations, how it is varying with respect to x1, then I will know how that rotation also takes place if this assumption were valid. But now that assumption is violated, that's not valid, and therefore that additional deformation that you're going to have, Timoshenko said, let it be called as a additional degree of freedom. So originally we had only 4 degrees of freedom. One is because of extensional load, there could be a translation about x1. Then there could be a torque, because of which there could be a rotation about x1, right? In addition, you talked about 2 bendings about the x2 and x3 directions, which are causing translations in these 2 directions. And we are saying that that rotation, because of this assumption, is not an independent degree of freedom. It is related to how that translation u2 and u3 vary with respect to x1. So the derivatives of u2 with respect to x1 or u3 with respect to x1 will give you that. Now Timoshenko said that all rigid bodies should have 6 degrees of freedom, 3 translations, 3 rotations. You are taking only 4, only 1 rotation, and you are taking 3 translations, and you are saying that the 2 rotations are dependent on that. Let me take 2 rotations. But what he forgot is this word over here, that it is like. It is not a rigid body degree of freedom, it is a rigid body like degree of freedom, and therefore in reality it can be mathematically very rigorously shown that a beam will beam's cross section will have only 4 degrees of freedom. Those 4 which Euler and Bernoulli took, in spite of their simplicity, were actually true. But how do you account for those additional 2? You don't need to take 2 degrees of freedom, but once you allow for this warping, that is the cross section to deform in its own plane or out of plane, and also those 2, then you would see that you can account for that rotation as well. Okay. Now, so these are 2 different paradigms. One, the reason why there is a problem with the Timoshenko model, he himself recognized, and that's why he introduced this thing called the shear correction factor. So he found that the end result is not agreeing wherever, let's say, theory of elasticity approach was there or experimental results were there to validate. He was finding that it was different, and for different cross-sectional shapes that he was trying out, he found that many different error sizes were occurring, and therefore he introduced this concept of the shear correction factor. But once you allow only 4 degrees of freedom and take into account the other 2 rotations, so-called transverse shear, within the 3D warping, then you would see that there is absolutely no need to make those shear correction factors and many other things that are typically like curve fits that you're trying to do. You're finding that there is an error and trying to fit it with the reality, either an experiment or a theory of elasticity where it is feasible, and then you're trying to see what is the correction factor. So you don't need such correction factors. So that is the approach that we will be outlining in the rest of this course, where we will be talking about leaving behind these kinds of assumptions which are risky, dangerous, which is why it is in red. Not that it doesn't work always. There are situations, simple textbook-like situations or preliminary design where you just want to get ballpark values just to get a feel for the problem. Then you can make this. The important thing there is the simplicity. You can do it very fast. Maybe you don't even need a calculator, just a back of the envelope kind of calculations. You should be able to do many of those things and you will get the answer. So that is the reason why that continues to be used. But in more and more advanced applications, and especially when you're looking at actual flight vehicle design or flight vehicle analysis for various reasons, then you have to go for more reliable theories which do not make those violations. We listed about 3 violations for plane stress. Those are the 3 main violations. There could be other violations as well. But similarly, the Kirchhoff law also causes many problems, just like the Euler-Bernoulli causes problems, which we just discussed. And therefore, you may or may not want to take this kind of an approach forward. You could instead, see, the whole idea is that this is all the thing. These are all unknown quantities. You're required to find those out. But now you're saying that, yes, I have to find it as a function of x1, x2, x3. It's very difficult for me to find it as a function of 3 variables. With respect to one of the variable, let me assume. So if a student were to do this, it would be considered as cheating. But when somebody, a researcher, does it, it's taken for granted, and especially when they have a lot of publications and following after that. And many people have made a whole career by just adding one term. For each term they add, they publish one more paper or another chapter in a book with a new edition of that, a new lecture series and things like that. Whole lot of people have made an entire career by just the number of terms that they have been adding it, and the whole, if you look at all of their publications, some of them are just related to this, and or changing the boundary conditions of the problem. Instead of a cantilever, go for a simply supported, go for a overhang simply supported, etc. So keep on going like that. Well, it's an art of furthering your career. That's one kind of an approach, but there can be a way in which you can solve this problem once and for all, and then take each one of those as special cases and see that, depending upon a particular problem, which level up to which you want to apply that model to. And that is the approach that we will study in this course without going into the details of its derivations and all that, which is a little complex and beyond the scope of this course, but we will go to the end results of that. And in another course, the nonlinear mechanics of composite structures, we'll be talking about the actual derivation of that theory and see how those results which we are presenting over here, how they are arrived at. So we will separate it in that way, because not all of you are going to eventually be structural engineers. You're going to be in many different fields, but you should be aware of what is the state of the art in structures, aerodynamics, controls, and propulsion, all of them. Because as aerospace engineers, you should have that overview of what is the current state of the art instead of what was done 100, 200 years back. Well, there are certain things which were done 100, 200 years back which are still very valid. So if they are valid, well and good. It's not just because it's old you leave it out, but because you recognize there are certain issues associated with that, some of which we listed out already. So can you do away with that? In other words, are the assumptions necessary and are they relevant? And you would see that many of these assumptions are neither necessary nor are they relevant, and therefore you might as well do away with them and deal with much better ways existing that you can apply for the same problems. So are there any questions till now?
Sir, does the plane stress state actually imply the other one also?
Yes. So it's actually a follow-up. So as I think you were not there in the previous class, what I'm talking about is when I make each one of these assumptions, I'm not making it an independent assumption. I'm accumulating the assumptions. So to this, I'm adding this, then to this, etc. So I'm building up. In other words, the class of problems that I'm looking at, I'm just making it as smaller and smaller subsets within that and going into. So you're absolutely right that this requires this. So it's in plane stress that we are bringing in this particular assumption. Yeah. Anybody else? Okay. Yeah, I think there's one more thing associated with this we should do. So if you remember in the previous class, we talked about So the void notation that we introduced, and once all of these 6 assumptions were in place, we had so this is these are the independent coefficients in terms of which we had derived in the previous class. We had written it the other way around with the strain on the left hand side and the stress on the right hand side, so that we could write instead of the C is the inverse of the C matrix in terms of the engineering constants, which included EL, ET, mu LT, GLT, and either GTT prime or nu TT prime. Okay, either one of them is good enough, because once you have the one, you can derive the others, as we saw in the equation last time. Now, 1, 2, 3, 4, 5 variables that we are talking about. Similarly, you have here 1 variable, 2 variable, 3 variable, 4 variable, and the 5th variable over here, right? So you have only 5 variables associated. Either you're talking of the stiffness or you're talking of in terms of the compliance matrix. Now, this particular thing, all these zeros that we got were primarily from orthotropy in the principal material direction. So time and again you need to stress that this 1, 2, 3 system that we are using is along the axis. So it's valid, for example, in this top ply alone, where you have, let's say, x1 along this and x2 along this. So you see that for the top ply, x1 is perpendicular to the fiber and x2 is parallel to the fiber, or the other way around for this bottommost ply. For the bottommost ply, you would have x1 along the fiber. So you see the cross section over here, circular cross section, and it's a straight fiber over here. So you see for the bottommost layer, you would have x1 parallel to the fibers and x2 perpendicular to the fibers. So for such a situation, you have this kind of a thing. In other words, it's the principal material directions that we have introduced the structural coordinates. So your x1, x2, x3 are the structural coordinates, whereas xl, xt and xt prime are your principal material coordinates associated with each ply. They could be in different directions depending upon the actual orientation of the fibers in that particular ply or lamina. Now, so that is as far as the zeros are concerned. Then in terms of why these two became equal, these two became equal to each other, and these two became equal to each other, and this was C44. Sorry, this should be C5, either C55 or C66. Okay, so this was C44, so let me not confuse that. So this is either C55 or C66, those two are equal to each other, and C44 was given in terms of the difference between these two divided by 2, which is similar to G equal to E by 2 into 1 plus U, which is what you're doing as an assignment right now, right? Now, the fact that you have 5 coefficients is in a 3D model. So this is still a 3D model where we are taking x1, x2 and x3 directions into account, but the simplicity what either Euler-Bernoulli and or Kirchhoff-Lau came up with for plate or shell theories or beam theory is in terms of getting rid of the third direction, which is the thickness direction over here. So in this particular case, the thickness is this x3 So to have a dextral triad, so that you have x1 b1 cross b2, where b1 and b2 are parallel to your x1 and x2. In other words, tangential to your coordinate curves x1, x2, your x3 has to be downwards because b3 has to be downwards. Now, if you want to eliminate that b3 direction, you see that those three stresses that are associated with that, which we called as sigma I3, are essentially these three stresses, all of which in a plane stress state are assumed to be 0, right? So if they are assumed to be 0, then it's very clear that these corresponding three strains that you have over here, I have an equation for each one of them. It's a simultaneous equation that I can solve for gamma 33, gamma 23 and gamma 13 in terms of gamma 11, gamma 22 and gamma 12, which is what we called as these three, remember, we called as the in-plane strains gamma alpha beta, whereas these three are your gamma I3s, right? Now your gamma I3 can be found as a function gamma I3 of your gamma alpha beta by solving these three simultaneous equations. The left hand sides are all 0, so you can solve for gamma 33, gamma 23 and gamma 31 in terms of gamma 11, gamma 22 and 2 gamma 12. Okay, so that means that I can then substitute that gamma 33, gamma 23 and gamma 31 in terms of gamma alpha beta and can rearrange this whole thing once again into a just instead of a 6 by 1 column matrix, I can reduce it to just a 3 by 1 column matrix involving only the gamma alpha betas. And here also, these are already gone anyway. I am left with only three stresses that I have over here, that is sigma 11, sigma 22 and tau 12, and I can express all of them in terms of your gamma alpha beta. So that is one of the biggest simplifications that result out of this whole exercise of the plane stress along with the Kirchhoff law hypothesis that you eventually make. And then what you would do is this gamma alpha beta, using the Kirchhoff law assumption, you would replace it as your epsilon alpha beta plus x3 rho alpha beta, where it's understood that epsilon and rho are functions only of x1 and x2. So this becomes the in-plane strains of the reference surface. In many cases, you might choose the reference surface as the mid surface, but it is not necessary. It could be for various practical reasons, depending upon either the aerodynamics or even structural reasons, you might choose some other surface as the reference surface. Doesn't matter, it's only the intermediate results which will vary. Your final 3D results, when you recover all of your three-dimensional displacement field, strain field and stress field, they would be one and the same irrespective of what reference surface you use. The reference surface choice, just like in the case of a beam, the reference curve, you could choose it, let's say, the intersection of the neutral axis in the two directions. You could choose it as the loci of the shear centers. You could choose it as the loci of the centers of twist. You could choose it as the loci of the aerodynamic centers of the airfoil. So you could even, in the case of a plate, instead of the mid surface, you could choose either the top surface or the bottom surface. It could help because you might know the loads coming from the aerodynamics on the top surface, that you might want to use that as the reference surface. Doesn't matter at all. Just be consistent in your entire derivation. Make sure that the same reference surface is used in all of your derivations. That's all that, that matters over there. Now, here in the case where you have this kind of expression, it's very clear that if x3 equal to 0, you get the reference surface. So epsilon alpha beta is, or your other way, gamma alpha beta is equal to epsilon alpha beta for x3 equal to 0, right? So in other words, for the reference surface, if I want to determine the in-plane strains, all that I need to do is to look at epsilon alpha beta. And what is rho alpha beta? It is the curvature of that reference surface. It is the bending curvature in one direction, bending curvature in two direction, and the torsional curvature that you have, which is what is the rho 12. So rho 11 is your bending curvature about the one direction, rho 22 is bending curvature about the x2 direction, and rho 12 is the torsional curvature that you have. So what we would do, the next step is, first, as I said, we will solve for these, substitute these in terms of gamma 11, gamma 22 and gamma 12 over there, and then leave out those three columns and rows corresponding to the third direction. So you have just a 3 by 3 matrix for the stiffness, 3 by 1 for the stress, and 3 by 1 for the strain. And in that 3 by 1, we will now substitute whatever remaining strains are there, gamma 11, gamma 22 and gamma 12. I would substitute in terms of epsilon 11, epsilon 22, epsilon 12, 2 epsilon 12, and similarly rho 11, rho 22, and 2 rho 12. So once I substitute that, I can then integrate that with respect to x3 to get the, instead of the stresses, what we call as the force per unit area, if we integrate with respect to the thickness, it becomes force per unit length. So instead of sigma 11, sigma 22 and tau 12, we will get new quantities which we will call as N11, N22 and N12, whereas all of these are Newton per meter squared, the stresses. The N's are all Newton per meter. In other words, you are integrating that with respect to the x3 or the 3 direction. Now what does that actually mean in terms of this particular laminate? Let us say what it means is that there is a stress that is there over here on a small area which we call as sigma 11. Now we are integrating that sigma 11 over the thickness x3 direction from minus h by 2 to plus h by 2 if the reference surface was the mid surface. Otherwise, if it is as I have shown on the top surface, it would be an integration from x3 is equal to 0 to h, which is the total thickness of this particular laminate. So whatever that is, when I integrate that, I am going to get, instead of the force per unit area, I am going to get force per unit length, and that length that we are talking about is the length along the breadth over here. So in other words, you have a distributed load over here, which I can show something like this along the x2 direction. Now as a function of x2, you have something that you are going to call as your N11, which is a function of your x2 direction. So in general, of course, it's also a function of x1 because I can cut this whole same thing at different values of x1. So it's a function of x1 as well. So it is the equivalent conjugate of your epsilon alpha beta. Remember, we talked about conjugates when we introduced the second Payola-Kirchhoff stress and the Green-Lagrange strain. So we said that if you insist on using Green-Lagrange strain, you have to go for the second Payola-Kirchhoff stress. You can't use any other stress because it's only as a combination, those two will give you the strain energy. More specifically, we have to talk about the actual specific, instead of specific energy, the specific power that we have to talk about. But because we are not talking of things varying with respect to time, that is the strain rates, etc. We are talking of either statics problems or low frequency dynamics problems. In other words, we are leaving out things like impact or very high frequency vibrations, etc. So in such situations, these are two very standardized stresses that are used, Green-Lagrange strain along with, which is a quadratic strain essentially, and then you have the second Payola-Kirchhoff. So those two are called as conjugates of each other. So the conjugate of Green-Lagrange strain is the second Payola-Kirchhoff stress and vice versa. So similarly, that is at the 3-dimensional level. So those are 3D stresses and 3D strains. Now we are talking of a 2D strain and a 2D stress. So when we talk of a 2D stress, it's no longer in pascals. It is Pascal meter or Newton per meter, right? So that is what we are talking of as N11 here. Similarly, on this surface, you would have an N22, which is varying along x1, and at different values of x2, if I cut, it varies along that as well. So it's a function of x1, x2. Why are we calling these as 2-dimensional strains and 2-dimensional stresses? Because they are functions only of 2 spatial coordinates, x1 and x2. They are not a function of x3, right? And corresponding to rho alpha beta, we will introduce another quantity which is called as m alpha beta. Just like n alpha beta was introduced there, now you will introduce moment per unit length, that is both 2 bending moments per unit length and a twisting moment per unit length. All that you would do is, instead of directly integrating with respect to the thickness, you will also involve a particular moment arm and then you will integrate with respect to that. That is, the moment arm is of course Z, and therefore once you get that, you get a M alpha beta, which is the stress conjugate of your rho alpha beta. So rho alpha beta are the, as I repeat once again, are the curvatures, the bending curvatures, rho 1 1, rho 2 2, and rho 1 2. These are the bending curvatures and twisting curvatures of the reference surface, and these are the moments per unit length applied to that reference surface distributed along the x1 and x2 direction. So just like the ends, these are also functions only of x1 and x2. In other words, these are also generalized two-dimensional stresses. So there are two kinds of stresses we are talking of, entirely different units. One is in Newton per meter. This is having just the unit of Newton, right? So because it's integrated, it's multiplied with a Z and then integrated with respect to Z. So then you therefore end up with the same unit as force, which is what you have over there, right? Now, or you can think of it, if you want to look at it as moment per unit length, you're essentially talking of it as Newton meter per meter. So that's essentially what it is. A moment per unit length and a force per unit length is what you're dealing with here, and those are the conjugates of these two. So then what would happen is, I'm substituting for these gammas as this. So now I can I'm also doing this integration. I'm interchangeably using x3 and z, x, y, and z coordinates, but it's the same. So the integration with respect to x3, once you carry out, you started off with a 6 by 6 matrix, you reduced it to a 3 by 3 matrix. Now by introducing this and putting your epsilons and rhos separately, once again you will have a 6 by 6 matrix. But what is the advantage you have got to in terms of the simplicity over there is that you still have a 6 by 6 matrix, but all the variables now, that is your n's, m's, epsilons, and rhos, are all functions only of two spatial coordinates, x1, x2. Earlier you had the sigmas and gammas were all functions of all three spatial coordinates, x1, x2, x3. In other words, instead of three-dimensional variables, you're going to two-dimensional variables, and when we go to their governing equations, you will see that they will still remain partial differential equations, but with one less independent variable, and therefore a little easier to solve compared to solving the original 3D elasticity equations, which involved all of the 3D variables. Are there any questions or doubts on this so far?
So one of the assumptions we made was on the Poisson's ratio effects not being there in the Kirchhoff law assumption.
Correct.
So wouldn't that mean that when sigma K3, tau 23 and tau 31 is 0, then the equivalent strains also should be 0 if the Poisson's ratio is 0?
No, see, there are two ways of looking at it. We talked about assuming the deformation not throughout the beam, but in terms of how the cross section behaves. Whereas in the other direction, how it behaves, we are still allowing it for. So it's here and there. It's not that we are completely leaving out all of the Poisson's effects. We are taking that into account in an indirect way. And good that you brought up that point, because there's a way in which people using these kinds of theories work back, because they now know that these are going to give problems. They're not going to solve the boundary conditions. They're not going to be useful for delaminations, etc. Once they get all these solutions, they'll go back to the three elasticity equations, the equilibrium equations that are there. And in the equilibrium equations, the last term on the left-hand side is essentially your the sigma I3s, comma 3, which you had dropped off. Now you can solve for those equilibrium equations also will not be satisfied exactly because of the wrong assumptions we have made. So we will depend on that equation to calculate your sigma I3 by integrating with respect to x3 your derivatives of sigma 1 1, sigma 2 2, sigma 1 2 with respect to x1 and x2. So it's a roundabout way of trying to get to it, and usually you will have a lot of errors there also because there are numerical differentiations involved, numerical integrations involved. Already because of the erroneous assumptions you have made, your sigma 1 1 2 2 and sigma 1 2 are slightly wrong. Now you're doing numerical integrations and differentiations over that. You're going to increase the size of your error. It can be mathematically proven that eventually you will get certain values, but still they'll be quite way off from what you can probably measure in using, let's say, you put strain gauges and or let's say Teflon layers in between on the over that you use the strain gauges to work back and look at these stresses, you would see there's a big mismatch that is typically happening. So in other words, there is a lack of consistency also, which is what you pointed out when you say, yes, I'm ignoring the Poisson's effect as far as the cross-sectional deformation goes, but once in the matrix that is there, I'm using those Poisson's ratios because I'm not taking C12, C23, or none of these I'm taking as zeros. I'm actually taking their values. So partly your certain parts of the derivation you are assuming 0, certain parts you are not assuming 0. So there's that lack of consistency also, which is what lacks that mathematical rigor as well. Yeah, anybody else? Yeah.
So the plane strain condition also.
Yeah.
So usually where it will be invoked?
Yeah, good question. See, they're kind of related because we are talking of the I3 components. In one case, we are talking of sigma I3 going to 0. The other case, we are talking of gamma I3 going to 0. So whatever we were saying, everything gets reversed. Now, in terms of where it is actually applicable, you have to see in terms of where gamma I3, what are the situations in which gamma I3 can be 0. So essentially what you're talking about is that you're trying to keep, for example, first one element, in the simplest element is your, let's say your gamma 33, right? So now let's take the 3 direction along this, right? Now the 3 direction is along the length of this. Then what I'm saying is that I'm applying boundary conditions such that this, I'm not allowing it to change its length, either decrease or increase. So I'm holding like that. The next thing is in the 3 direction, I'm not allowing for shear strain gamma 1,3 and gamma 2,3. In other words, right angles on this, I'm not allowing it to change. So that is the other thing that we are trying to do. Now, once, sorry, not on this and this, because this is the 1,2 plane, and therefore the shear strain on this is gamma 1,2. That is allowed. Now, what we are not allowing is the shear strains on this and the shear strains on this. So a typical example you would have also come across in plane strain is the dam, for example, where you know that the dam, if the water is flowing between you and me, you're essentially keeping it like this, blocking the water, and therefore the load is coming over this, and this has columns which are holding it tight over here. In other words, it's not allowing it to change its length over there. So your gamma 33 equal to 0. Now the question is, how accurate is your gamma 1,3 and gamma 2,3 being equal to 0? That's where typically, once again, the plane strain also gets into slight problems. That's why it's not as accurate as a 3-dimensional model. It shouldn't be, because it's a dimensionally reduced model, and no dimensionally reduced model, however well you do, will be exactly matching. But still the errors are much larger than what you would be happy with typically for engineering purposes, and that's the reason why that is not a valid argument once again. So in terms of, this is just an example that everybody knows, the dam example. But in a general case, how do you know whether it is a plane stress or a plane strain? You have to go to these definitions. You have to check your gamma I3s and your sigma I3s, which you will not know a priori. Those are the unknowns of your problem. You have to determine them. So unless and until you determine them using some other approach for a specific case, then you can, with that knowledge, you can come back and say, yes, this is a possibility. But if you know anyway, either one of this being 0 or this being 0 are getting violated, you cannot use either a plane strain or a plane stress problem. So this is the final check that you can have. There can be intermediate checks based on the fallouts of this, like what we are talking about in the Kirchhoff law, where let's say the in-plane strains are linear in X3, etc. Those are all kind of fallouts, but the real check is always to go back to your definition and check whether it is getting violated, or in most cases it will be getting violated, but at least is this small, negligible compared to the other 3 stresses, then yes, it's a plane stress. Similarly, these 3 strains, are they negligible in all? You take the maximum value of them in the entire domain of the structure. Is it small compared to the maximum values of the other 3 put together? So then, if it is, yes, maybe it's a reasonable approximation to do, especially for preliminary purposes, but otherwise not. Yeah. Okay. So,
Usually the fracture toughness testing,
mhm.
we usually do in only plane strain condition.
Mm.
So that like what is the theory or whatever this is there. In plane stress we are not able to get the consistent values.
Right.
So what is the reason behind it?
Yeah, see, the fracture toughness is essentially your stress versus strain, right? So when you're taking the stress versus strain, remember that the boundary conditions that you're having in a typical system, let's say in a UTM, is that you're allowing for the strains in the other direction to be free. In other words, it's a free edge. So you're allowing for those strains to go to zero, right? So, the stresses to go to zero. So which is how we populate the compliance instead of the stiffness matrix. That is how we get that, right? Now when you're going to the extremes, the change in cross-sectional dimensions are going to become so large that unless and until you are having certain plane strain-like conditions, you will not be able to get that area under that curve correctly, because towards the later end of that curve, going to closer to failure, you will not get accurate results because your cross-sectional geometry is changing so much. Right? So with a plane strain, you're trying to maintain that cross-sectional geometry, and therefore you're getting that. So again, it also depends upon what kind of stresses and strains you're associating with, because true stress and the stress that your different definitions of stresses are there. So depending upon which stress and strain combination that you're going to, there could be possibilities of if you have ways of measuring certain types of strains, you could do with a plane stress kind of a thing also. But in most situations, the simplest way to accomplish that in an experimental result is by using the plane strain approximation, where you can have much more accuracy. But you typically don't use that to determine, let's say, just the Young's modulus and things like that, because the plane stress condition is not the plane stress, but the condition associated with the free boundaries is much easier than to constrain the outer boundaries and do the experiment. So it's all a question of what is the end result that you're looking at from the experimental point of view, and what are the complications that are there in terms of the post-processing of those data that you collect in order to get those takeaways. So based on that, you take a call.
So also, I think for the plane strain
Yeah.
toughness,
Uh-huh.
it's mainly because when we go for a lower range of thicknesses, the stress triaxicity comes into play, and the fracture toughness we get is much higher.
Mm-hmm.
Generally, when we do an experiment, we tend to go towards the level where it's nearly asymptomatic.
Mm-hmm.
Like, I mean, if you look at the fracture toughness versus thickness, it's a downward
Mm-hmm.
decreasing curve
Mm-hmm.
which actually stabilizes.
Mm-hmm.
So usually we tend to go to look at that which is a stable value.
Mm-hmm.
So
Mm-hmm.
even if we are changing the thickness, we get a similar consistency.
Mm-hmm.
Otherwise, because we look at a lot of NASA tests, we see that the fracture toughness of materials is much higher than what we generally give in literature. So
Okay.
that's also
Okay.
one of the main reasons.
Sure. Yeah. Thank you. Yeah. Anything else? Yeah. So I think you can go to one more. Yeah. So the other thing is kind of, again, as you said, related from one following from the other. And for example, in this, we assume the strain field. So that takes over in terms of many people assuming the displacement field. So the displacement field, for example, in a plate would be assumed to be in the simplest situation, you would take your U1, which is in reality a function of all three spatial coordinates. You take it as just U1 naught of x1 comma x2 alone. Similarly, for your 2 direction as well, okay? And your 3 direction, you would typically take it as a gamma 3, which is a function only of x1, x2 multiplied by x3. So in other words, linear in x3. So in other words, you're taking your gamma 3 definition itself to lead to your U3. So in other words, not only are you making certain restrictions on the strain, you're making certain restrictions on the displacement. And there have been a whole body of literature which has followed by people, because people complain that this is not right thing to do, this is an unknown quantity and you're taking how it depends on X3 a priori. So in other words, it could lead to errors. So they left out these, but instead what they were essentially doing is to make assumptions on the stress field, which is also an unknown quantity. So instead of making assumptions on the displacement, they started making assumptions on the stresses, that is your sigma 11, sigma 22 and sigma 12, how they vary with respect to X3. So that was assumed and then it was taken forward. So the whole point that I'm bringing out in all of this is that these are all unknown quantities, whether you're talking of the strain, the displacement or the stress. None of them should be assumed even in the smaller direction, which is the X3 direction. They are truly unknown quantities and they have to be determined that way. So, and there are rigorous ways of determining that. Mathematics has progressed so much in the last century that 50 years ago we have already been able to do this. That is, without taking any of these assumptions, we could derive that. But just that we've been blind to that small body of knowledge. Everybody is progressing in a particular direction. Everybody else follows that particular direction, and that's the reason why you find a lot more literature like that, and many of them have gotten into textbooks, and that's what students are taught at undergraduate and even in master's level programs many a times, and they continue to do that when they get into the industry, and therefore that wrong path has been set very early on and it has continued for a long period of time. So which is what we will try to leave out in the rest of this course, where we will try to avoid this. Now, in addition to that, of course, the shear correction factor is one example. There could be many other empirical formula that come up for various other parameters as well, and all of that is coming primarily because you have made certain wrong assumptions about the unknown quantities, which may be valid in certain specific special cases, which is why we call them as ad hoc assumptions. So we refer to such assumptions as ad hoc assumptions. Where this adjective essentially means that it's not that it's not valid, but it's valid in some special cases. But you're then taking that as the reason for it to apply it to more general cases where it may not be applicable, and that's the problem. So those ad hoc assumptions is what we want to give up, so that we don't need to end up doing some empiricals where the physics and math itself is sufficient to lead us to the results. Still, there are of course a lot of works that still are not to rigorous physics and math as of today. In such cases, yes, where you have no other way, yes, you can rely upon empiricals. Now, we have nothing against empirical kind of approach. In fact, if you look at all of machine learning and artificial intelligence today, it's all based on big data, and you're essentially bringing in, instead of the physics dictating it, it is the data which is dictating it, which is essentially some kind of empirics in a more refined fashion, that or in a different terminology, it's coming up. But the idea of having a physics-based model is that it gives you a lot of insight into the problem. You understand the physics of the problem, you understand many other repercussions of that, and not only the design decisions that you're going to make for that particular problem that you're going to solve, but in terms of takeaways of your knowledge for applying to entirely different problems, because you know how the physics works over there, so you can take that forward. So that is the reason where even between numerical solutions and analytical solutions, when you can, certain cases have just pure analytical solutions, you must try and extend the limit to get those analytical solutions. Today, with today's computations, computational power, both in terms of software and hardware, that might be thought to be silly. But the insight it gives, especially when you're doing more of either an academic research or a research into something which is of long-term benefit, then always it helps you, where feasible, to go for without assumptions or minimum number of assumptions, and with analytical techniques to the extent that you can push the limit. And then when you cannot do that, which are a huge number of cases, a lot of practical cases in engineering, then you go for the numerical techniques and the various other things like machine learning, artificial intelligence, etc. Just because these are like keywords today and it's a fashion, become fashionable for getting jobs, etc. Everybody throws this. And if you look at most of the works that have been published based on ML and AI, they can be done very easily even without ML and AI. It's just that it's being applied to that particular problem. But there are still a huge number of problems where you cannot do it with the today's level of physics and math. There, you can use such kinds of big data tools, especially you have access to such large data sets, relevant data sets, then you can use that. So that's the whole idea of seeing when and where to use the various potential tools that you have, not blindly use it in each and every case just because you have the power of using large computations. Okay, so I think with this we come to the end of all the assumptions that we have made. In the next class we will try to take up an exercise which I've always found to be very useful in this particular course, where we try to get from you the inputs in terms of all the kinds of variables that you have used in your structures courses, be it in strength of materials, theory of elasticity, or any other materials course, or even your GATE exam, and various other textbook problems that you would have seen or research papers that you would have read. What are all the variables that are involved in your structures paradigm? That is, in terms of what are the known quantities, what are the unknown quantities. When a question is framed, obviously there are certain known quantities, there are certain unknown quantities, and you use certain equations to bridge those two, and you calculate the unknowns in terms of the known quantities. That's how you typically solve problems, right? So we want to get collect all those variables, whichever you remember at that point of time. In the next class, we will list them out, and then we will see, is there a way of bucketing those variables so that we can understand the large framework instead of looking at each one of these as individual problems and each one as a new body of knowledge that you're learning. No, it's all fitting into a particular framework as far as structural mechanics is concerned, and that will help you in the future when you learn new things to see where those things fit into that overall paradigm, and it will help you to very quickly grasp newer terminology, newer kinds of behaviors of materials, newer types of materials, etc. So keeping all that in mind, we will do this bucketing exercise in the next class. I'll just ask each of you to name a few variables, some knowns, some unknowns, some constants that you have used, some equations that you have used, and we will all put them all together. There might be some of these which may not be exactly bucketed in one particular type. They might stretch, but most of them get bucketed in certain ways. Once we finish that exercise, I'll bring to your notice what those buckets are, and then you will see the connectivity between them. And once that settles deep in your mind, structures will look very, very different from the way you have looked at it before, because it helps you to understand everything from that framework, and then many things which you initially thought to be complicated, you will find to be much simpler than that. Okay, thank you.